Hello, my name is Desmond Edagisi, and I'll be your maths teacher for today's class. Today we'll be looking at the theme Numbers and Numeration, and under Numbers and Numeration, we'll be learning all about sets. Our topic under sets today is operations on sets. It promises to be an interesting class. Let's go on. At the end of our class today, we'll learn that there are certain operations that take place between sets. One of such operations is the union of sets. Also, we'll learn about the intersection of sets. And lastly, we'll learn about differences in sets. Let's go on. The union of sets A and B, written as A union B, is a third set that consists of all elements that belong to both sets. The symbol is used to denote the term union. Let's take an example to better understand what the union is. If we have a set that has as its elements 1, 2, and 3, and we have another set that has elements 2, 3, and 4. The union of both elements is a combination of all the elements present in both sets. If we listed out the elements present in both sets, there will be 1, which is found in our first set here, 2, which is found in both sets but represented as just one element, 3, which is also found in both sets but also represented as just one element, and 4, which is found in our second set. Let's take another example. If A is the set that has elements 1, 3, 5, and 7, and B is the set that has elements 1, 2, 4, and 6, union of both sets would be a set that has all the elements found in A, inclusive of the elements also found in B. Let's list them down one after the other. We have 1, which is found in both sets but represented as just one element. We have also 2, which is found in our set B. We have 3, which is found in our set A. We have 4 from set B. We have 5 from set A. We have 6 from set B. And we have 7 from set A. Let's take another example. If A is the set of all x such that x is an even integer larger than 1. If we listed out our set A here, would have even integers 2, 4, 6, 8, 10, 12, and so on. It goes on and on forever. We say our number ranges to infinity. If we also have the set B, which is the set of all x such that x is an odd integer number larger than 1, would list the elements of our set B as 3, 5, 7, 9, 11, 13, and so on. Again, our set will tend to infinity. The union, therefore, of our set A and B, that is A union B, would be a set C that has as the member of its set the elements that are present in our set A here listed and our set B. Let's take a look at our set A. Elements in set A, 2. From set B would be 3. From set A again, 4. Set B, 5. Set A, 6. Set B, 7. Set A, 8. Set B, 9. And so on. Again, our set will tend to infinity. One quick fact to take note of is sets cannot have duplicate elements. Let's take a quick example. If we have a set that has as its elements 1, 2, and 3, while we have another set that has as its elements 2, 3, and 4, the union of both sets here would be the elements present in our first set here and also present in our next set here. That would be a set that has element, for instance, 1, which is from our first set, 2, which is present both in our first set and the second set. We have the same elements being repeated twice, but in our union set, we would write 2 down only once. Again, if you notice, we also have the element 3 present in both sets, but in our union set, we'd write it down just once. And then we have 4. So once again, sets cannot have duplicate elements. Let's take a look at some practical examples for better understanding. The members of a JET team form a universal set. The universal set has as its elements Ada, Femi, Chike, Grace, Salimatu, Ali, Dele, Obilor, Emeka, and Tayo. If set A is the set of all students whose name end in A, set A will be listed therefore as the set that has elements Ada and Emeka. Also, if set B is the set of all students with 4-lettered names, B will be listed as the set that has elements Femi, Dele, and Tayo. If set C is the set that has students whose name begin with an S, C would have elements Salimatu only. Now we've been asked to list the sets of the union A and B. So A union B would be a set that has elements Ada, Emeka, all from our set A, and also Femi from set B, Dele from set B, and Tayo from set B. That's our union. Also, we've been asked to list the union of the sets A and C. A union C is the set that has elements Ada, Emeka, all from set A, while we have Salimatu from set C. Also, we've been asked to list the elements of the union B and C. B union C would give us the set that has elements Femi, Dele, Tayo, all from the set B, and Salimatu from set C. And there you have it. Let's take a look at our other example here. If our universal set is the set of elements A, B, C, D, E, and F, M is the set that has elements A, B, C, and D. N has elements C, D, and E, and the set P has elements B, D, and F. List the set of M union P. M union P would be the set that has all elements present in M and also in P. if we listed out those elements, there would be A, B, C, D, all from our set M. While we have P with elements F. We have elements B and D in P, but they are also present in M. And we learned earlier that we do not repeat elements in the union. So we have F, which is present in P, but not in M, and therefore we list it in our union. Let's try the other one. We've been asked to list the elements of the set that has M union, all in bracket, N union P. To do this, we'll first find our operation that is enclosed within the bracket, and that's N union P. N union P will be the set that has all elements in N and P. The elements listed in the set N are C, D, and E, while the elements in P are B. D is listed but is also present in N, hence we do not repeat it. We also have F. So we have N union P as the set that has elements C, D, E, B, and F. Let's go back to our question. Our question is to find the elements that are present in M union, all in bracket, N union P. We found N union P as the set that has elements C, D, E, B, and F. The union, therefore, between M and our union, N union P, would be the set that has the elements A, B, C, D, E, and F. Next, let's find the union between N and P. Of course, if we remember, we've already done that here. We have the union between N and P as the elements C, D, E, B, and F. So N union P is the set that has elements C, D, E, B, and F. And lastly, we've been asked to list the set M union N, all in bracket, union P. Again, we'll first carry out our operation on the sets in bracket. M union N is the set that has all elements in M, which are A, B, C, and D. While the elements in N are C and D, which are already present in M, hence it's not repeated, and E. So we have the elements of M union N as A, B, C, D, E. Now let's go back to our question. M union N, all in brackets, union P, therefore is the set that has elements A, B, C, D, E, and F from our set P. And there is our answer. Another very useful operation that takes place between sets is the intersection. The intersection of two sets is a third set that consists only of all the similar elements which belong to both sets. The symbol for intersection is like the inverted symbol that we use in the union operation. So if we have two sets A and B, if A is the set that has elements 1, 2, and 3, while B is the set that has elements 2, 3, and 4, A intersection B is therefore the set that has elements that are similar in our set A and B. If we listed out the elements that are similar or common, Between our set A and B, we would have 2 and 3. 2 is found in A and also in B. Also, 3 is found in A and also in B. Therefore, intersection of A and B would give us the set that has element 2 and 3. A quick one, we need to take note that the sum of the cardinalities of the intersection and the union of two sets is equal to the sum of the cardinalities of the two sets. Let's take a practical example. If we make use of our given set A here, which has elements 1, 2, and 3, and B, which has elements 2, 3, and 4. If we found the union between both sets, we would have a set with elements 1, 2, 3, and 4. If we took the cardinality of our set A union B, we would have 4. That is, the count of the unique elements within our union A union B is 1, 2, 3, 4. 4 elements. The cardinality also of our intercept A intercept B is a count of the unique elements within our intercept. If we did a count, we have 1 and 2. That's 2 elements. If we summed up our cardinalities, we have 6. Also, the cardinality of our given sets A and B. First, let's take the cardinality of our set A. We have what? 1, 2, 3 unique elements. The cardinality of our set B, which is the count of the unique elements in the set B, is 1, 2, 3. So we have also 3 elements. If we sum that up, we also have 6. So we have 6 elements and 6 elements on both sides. Therefore, our statement here is correct that the sum of the cardinalities of the intersection and union of two sets, which is 6, is equal to the sum of the cardinalities of the two sets. Let's go on. Let's take examples also to better understand the concept of intersection. The members of a jet team form a universal set where the universal set is the set of Ada, Femi, Chike, Grace, Salimatu, Ali, Dele, Obilor, Emeka, and Tayo. If A is the set of all students whose name end in A therefore will be listed as Ada and Emeka. If B is the set of all students with 3-lettered names, we would list our set as Ada and Ali. If C is the set of all students whose name begin with the letter E, we would have our list as Emeka. Now we've been asked to list the sets of A intersection B. A intersection B is therefore the set that contains all elements that are similar or commonly found in A and B. If we took a quick look at our sets A and B, we'll find that Ada is the element common in both sets. Let's also find A intersection C. Again, we have a set whose elements are all common or familiar elements in A and C. Once again, if we did a quick observation, we'd notice that Emeka is the common element. So, A intersection C would give us a set with elements A maker. Lastly, let's find B intersection C. That would give us a set whose elements are the elements that are commonly found in B and C. If we quickly compare the set B and C, we'll notice that they have no element in common. Therefore, this gives us an empty set, which we write as an open and close curly brackets that is empty, or simply 0 with a slash across it. So B intersection C is an empty set. And that's that for that. Let's quickly look at our second example here. If we have a universal set with elements A, B, C, D, E, and F, and we also have M with elements A, B, C, D, N has elements C, D, E, and P has elements B, D, F, we've been asked to list the following sets. First, we are to list the set that is the intercept between M and P. M intersection P would give us a set that is the elements commonly found in M and P. If we took careful observation of our sets M and P, we'll find that B is common between both sets. We also find that D is also common. So our intersex here is the elements B and D. Next, let's find M intersection, all enclosed in brackets, N intersection P. For such a case, you first find the operation within the bracket. So let's quickly do that. If we found N intersection P would have a set whose elements are common between N and P. Let's do a quick comparison of our sets N and P. The common elements that we have are D. And we have D only as our intercept. Therefore, if we come back to our question here, M intersection N intersection P, all enclosed in brackets, would be D, which is the set that both sets have in common. Next, let's find N intersection P. If we remember the question that we answered before now, we found our N intersection P, and we said we have the set that has the element D as its answer. Lastly, let's find the intersection between M intersection N and P. To do that again, we'll first resolve our operation that is within the bracket. Let's find M intersection N, which is the set that contains all elements common between M and N. The elements common between M and N are C and D. Let's go back to our question, therefore. M intersection N, all enclosed in bracket, intersection P, would give us, therefore, the set that has element D. D is the common set between M intersection N and P. D is common. So we have D as our answer. Another operation that is common in sets is difference. If A and B are two sets, then the difference of A and B is the set A minus B, which consists of all the elements which are elements of A but are not elements of B. Let's take a practical example. If we were asked to find A minus B, where B is the set that contains elements 1, 2, 4, and 6, while A is the set of elements 1, 2, 4, 6, 7, 8, and 9. The numbers seen in A that are not in B are 7, 8, and 9. So A minus B therefore is 7, 8, and 9. If you took careful observation, you would notice that A has 1, 2, 4, and 6. If we cross that out, 1, 2, 4, and 6, the elements we have left are 7, 8, and 9. Hence, we have our difference. Let's go on. Let's take some quick examples. If you are asked to find the difference of G and H, where G is given to us as the set that has element 3, 4, 5, 6, 7, 8, 9, 11, 12, and 15, while H is the set that has elements 4, 6, 8, 12, and 15. The difference therefore would be G minus H, which would give us all the elements that are in G but not in H. Let's quickly do a check. 4 is an element in G. Let's cross that out. 6 crossed out. 8 crossed out. 12 crossed out. 15 crossed out. Would have the elements remaining as 3, 5, 7, 9, and 11. So G minus H is the set that has element 3, 5, 7, 9, and 11. Let's take a look at our other example here. What is A minus B? Where A is the set that has elements A, B, C, D, E, H, I, J, L, U, N, and O, while B is the set that has elements A, E, I, O, U. Again, let's cross out our common elements. A is crossed out, E, I crossed out, O crossed out, and U crossed out. Our remaining elements will be B, C, D, H, J, L, and N. Therefore, A minus B is the set that has elements B, C, D, H, J, L, and N. Let's take a look at our next example here. Find M minus N, where M is the set that ranges from 1 to 10. If we correctly listed everything out, we'd have our set as that. N, meanwhile, is the set that has elements 1, 3, 5, 7, and 9. Let's quickly do a careful observation and cross out every common element. 1 is common, so we cross out 1. 3 is common, so we cross out 3. 5 is common, cross 5 out. 7 is common, we cross that out. 9 is common, we cross that out. So the elements left in M that cannot be found in N are 2, 4, 6, 8, and 10. M minus N is the set that has elements 2, 4, 6, 8, and 10. Let's take a look at our last example here. What is the difference of A and B? A is given to us as the set of all x such that x is in the range between 8 and 1. If we listed our set A out, we'd have 2, 3, 4, 5, 6, and 7. If we also listed out our set B, which is the set of all x such that x is in the range between 5 and 2, would have x as 3 and 4. Therefore, the difference A minus B is the set of all elements in A that are not in B. If we quickly crossed out the common elements, we'll have remaining elements as 2, 5, 6, and 7. 2, 5, 6, and 7 are present in A but not in B. So we list them as 2, 5, 6, and 7. And that is the difference, A minus B. In summary, we've learned that there are certain operations that are commonly found between sets. One of such operations are the union of sets. We said the union of two given sets A and B is a third set that contains all the elements that belong to both A and B. We also learned about intersection. We said the intersection between two sets A and B are every similar element that are present in A and are also found in B. And lastly, we learned about the difference. We said the difference of sets A and B is, for instance, the elements that are in A but cannot be found in B. With that, we've come to the end of our class for today. I'm sure you had a wonderful time. I look forward to seeing you in my next class. And from me, it's bye for now.